the commodity fibers, but those commodity fibers we have already discussed. But now onwards, we will be discussing three different types of fibers, which are the high performance fibers. Okay, so these are the industrial fibers where the usage in apparel is less when compared to the usage in apparel in the technical textiles. So in these high performance fibers, there are various fibers are there like aramid fibers. Under aramid, there are various types like Nomex, Kevlar, Twaron, and other fibers like high performance fibers like glass is there, ceramic is there, carbon is there. There are plenty of high performance fibers is there. High performance fiber is a separate chapter by itself, but in our syllabus we will be discussing on three different high performance fibers. One is the aramid, carbon, and then glass fibers. So in today's lecture we will be moving on to first start our lecture with the aramid fibers. So what is this aramid? Aramid, it is a short name for the aromatic polyamide. Okay, so there is a definition according to the FTC, that is the Federal Trade Commission. So aramid is the manufactured fiber in which the fiber forming substance is a long chain synthetic polyamide in which at least 85% of the amide linkages are directly attached between two aromatic rings. See here, the word you can see here, at least 85%. This is important. If you just compare this word at least with the other fiber which we discussed much earlier, that is the nylon. Both are polyamides. Nylon is also a polyamide. Aramid is also a polyamide. Whereas in the nylon, you see that is also a synthetic polyamide in which less than 85% of the amide linkages are attached to the aromatic rings. But whereas here, you see at least 85%. It means that minimum 85% amide linkages should be attached to the two aromatic rings. So the aromaticity is high in this aramid fibers. So there are two different and important categories that comes under this aramid fiber. One is the Nomex and Kevlar. Both these fibers are developed by the DuPont company from the USA. So there are other types of aramids also we will see, like nylon. This also have some nomenclature in classification, like you see AB type and AABB type, like nylon 6 and 6,6. Here also you see AB type is the polyparabenzamide. This is a aramid fiber. You can see here this is the amide group, and here this is the carboxyl group, where this is the benzene group, which is the polyparabenzamide. You can see here it is in the para position. Another one is the aromatic AABB polyamide. Okay, what is this AABB? This AA is the carboxyl. You can see here AA and BB, which is the NH and NH. Okay, so here you see this is in the meta position. I hope you may be knowing what is meant by ortho, meta, and para. If the two functional groups are attached very close without any gap, then that is the ortho position. If there is one gap, that is the meta position, and if it is diagonally placed like this, that is the para position. So you can see here this is the polymetaphenylene isothalamide. Okay, just to remember this name, it is the metaphenylene. This is the phenyl group here. Okay, so isothalamide, this is the amide here. Amide groups are there, two amide groups are there, so it is the isothalamide. Just to remember this name. There are two different types of aromatic AABB. One is the polymetaphenylene isothalamide and polyparaphenylene terephthalamide. There is a subtle difference here. You can see here the same OH and the C double bond one NH group is there. Only difference is the position. It is the meta position. Here it is in the para position. So here this meta position polyamide is called the Nomex, and the para position polyamide is called the Kevlar. So first we will see the Nomex fiber. So before going into discussion about how the fiber is manufactured, first we should know how this polymerization of aramids is done. Okay, so since I have told you in my earlier lectures on melt spinning also that this aramid fibers, they have a high melting point. Okay, because it's a high performance fiber. Okay, they have a high melting point, so it will degrade before it reaches the melting temperature. Okay, so for this normal polymerization, like addition polymerization, or if you see like a polycondensation, you cannot uh, do for this, because the precursors that you are using, that whatever amines that you are using for this manufacturing, they have the reduced reactivity, and also it has a very high melting point. It degrades before reaching the melting point. So for this react for this polymerization, you have to go for some low temperature solution polycondensation. Normally the polycondensation, if you see in the polyester manufacture, we use a high temperature polycondensation. We will do a preliminary pre-polymerization step followed by the high temperature polycondensation. But whereas here we do the polymerization by low temperature solution polycondensation. And you know that how this nylon or aramid is done. Normally an amine and acid will react to produce this amide. Okay, either an amine and acid will react, or an amine and acid chloride will react to produce a uh, amide, which can be a normal type of a polyamide, which is a aromaticity is less, and more aromaticity is there in the aramids. So here, the polymerization, how you do the polymerization, you need some solvent. Okay, you need some solvent, or some swelling agent is required to do the polymerization, and that solvents selection is important. You need an inert solvent. At least for one of the reactant, you need a inert solvent, so that you can perform the polymerization. So there are various solvents are used for this polymerization. For example, if you see, the preferred solvents are DMAC. You may have heard this name during the acrylic manufacture: dimethyl acetamide, N-methyl pyrrolidone, hexamethyl phosphoric triamide, tetramethylurea. These are the different solvents are there we are using. But why we are using these solvents? Because we need to control the molecular weight. Okay, we should not allow the molecular weight to increase. Okay, to have some control on the molecular weight, we need to add some specific solvents along with these solvents. Okay, so for this reason, we are adding some solvents like lithium or calcium chloride, so that the solvation power will be increased, so that the molecular buildup will not happen. Okay, because it's a high performance fiber, we need a controlled molecular weight to perform the polymerization. If you see here, this is the acetamide. You can see here CH3CON, dimethyl acetamide. You can see here, this is the dimethyl CH3. You can see here, when this solvent is mixed with lithium chloride, or you can say even you can use a calcium chloride also, so that what will happen from these metal halides, because if you know, this lithium is a metal and chlorine is a halogen. By this you get some positive and negative charge, because it ionizes. Okay, so what will happen, the polarity of the solvents gets increased by reaction with this solvent. You can choose any one of these solvents, like dimethyl acetamide, or a NMP, or a HMPA, or a tetramethylurea, so that what will happen, the polarity of the solvents get increased, so that you can perform the polymerization. So first we will see how this Nomex is manufactured. Then we will see how the Kevlar is manufactured. So Nomex, it is chemically called polymetaphenylene isothalamide. Okay. So how it is produced? It is produced by diamine and a diacid. You can see here, this is the diamine, because two amide groups are there with the benzene ring. You can see this is the diamine, and this is the diacid. You can see here, there is a carboxylic acid group. Either you can use a diacid, or you can use an acid chloride. Okay, this is a acid chloride. You can see here COCl. There are two COCl groups in the benzene. So these both reactants will react in the presence of a solvent to produce the Nomex fiber, which is the polymetaphenylene isothalamide. Okay, so here you can see here, the groups, meta oriented rings are there. You can see here NH, there is a gap and there is an NH, which is the meta structure. So this is called the polymetaphenylene isothalamide. Okay. Uh, so you can see here the amide groups are repeating NHCO, and here also if you see this is continued, there will be another NH and another benzene ring, so that it will be continued. Okay, this is the basic overview of how the Nomex is manufactured. If you see the fiber manufacture, what we do is first uh, we prepare the polymer and mix this with some solvents like inert solvent like lithium chloride or a calcium chloride, and then we do the spinning. If you see, you can perform, because since you are using a solvent, these solvents can be either evaporated or it can be separated out by either using dry spinning or you can use the wet spinning. For example, if you're using the dry spinning, then you have to circulate some hot air so that you can evaporate that solvent, so that by the one-way heat and one-way mass transfer, you can perform the dry spinning. Or if you want to do the wet spinning, you can do the wet spinning where you can extrude the filament, put it in a bath where there is a separate solvent is there. The fiber axis, so that you can get the good orientation and the mechanical properties. Now coming down to discussion on physical properties of Nomex fiber. Nomex, it's a strong fiber. Okay, unlike you compare with other synthetic fiber, Nomex is a strong fiber, and it has a high strength. You can see here 3.8 to 7.2 grams per denier, and it has a good elastic property, and breaking elongation is around 25 to 40%. And you see the density is close to polyester, around 1.38 grams per cc. And another advantage is, since this structure, if you observe, there is a more amide and carboxyl groups are there. You can see here both these groups are water loving groups, so it has some good moisture absorption property also. So it has a moisture regain of around 4.5%, close to nylon. Nylon has around 4%, and this also has 4.5% in the standard atmosphere. And one of the important thing to know from this fiber is, since it is a high performance fiber, and if you see the structure, at least 85% of the amide groups are attached to two aromatic rings. So plenty of amide groups are there in between two aromatic rings. So both the moisture regain is also there, and also aromaticity is high. Okay, so that leads to good flame retardant property. Okay, so this fiber has a good flame retardant. It is inherently flame retardant. What is meant by inherent? Means by its nature, naturally it is a flame retardant fiber because of the high aromaticity. And important thing to know is, it does not melt, but it will directly, before reaching the melting temperature itself, it will degrade. So it will degrade around, say, 400 degree centigrade. So you can say it's a inherently flame retardant fiber. Chemical properties are fair. It is has a good acid resistance, and even alkali and bleaching and solvent resistance is good, and excellent resistance to sunlight, mildew. Mildew is something like a fungus. Okay, so biological organisms cannot easily attack it, and it is resistant to aging also. So chemical properties are excellent. Application, yes, it is applied in technical, more towards the technical applications like space suits, where in the space, when the people are flying in the space, they use this Nomex type of a clothing fibers in the clothing, because Nomex fibers, this has an inherent flame retardant property and good strength also. So space suit you can use, and children's fireproof dresses, wherever the children needs protection, there they can use this fireproof dresses made up of Nomex fiber. Firefighter coats, racing drivers overall, wherever the car race people are using, where there is chance of any fire accidents to take place, there you can use this as a overall total garment is made up of this Nomex fiber. Then foundry workers clothing, then protective gloves and footwear, covering cloth over an ironing board. You must have seen there will be the table where we do the ironing. You see that covering cloth is usually made up of a Nomex fiber because it can sustain good temperature. And filtration, yes, in filtration, high temperature filtration, refinery operators uniform, automotive cushion material, hollow fibers for desalination by reverse osmosis. There are many good applications out there for this Nomex fibers. But there are some disadvantages also associated with the Nomex fiber. That is why some alternatives were suggested. So this fiber, though it has some excellent thermal resistance, but mechanical properties are not that high when compared with the other high performance fibers. Okay, because you see the structure is a meta-oriented aromatic ring. Okay, so it helps to process the fiber very easily. We can carry out the reaction with the diacid and diamine and perform it, but the problem is it does not give that much of a strength that is expected from the high performance fiber. So that is the reason where the research was done. Instead of using the meta-oriented structure, if we change it to para-oriented structure, that will lead to more intermolecular hydrogen bonding, so that what will happen, the fiber will be more crystallizable. Okay, so that is the reason why this meta-oriented aromatic rings were changed to para-oriented aromatic rings by using some different precursors where there is a change. Instead of using a meta-oriented precursor, we use a para-oriented precursor, so that that will lead to more intermolecular registration of the amide groups and make it more crystallizable, so that will stiffen the structure. Also, it lead to the good mechanical properties. Okay, so that is the alternative where the change of meta to para. So that is the Kevlar fiber. It is chemically called the polyparaphenylene terephthalimide, PPTA. It was also released by the same company, which is the DuPont, in 1972 under the trade name Kevlar. This fiber has outstanding modulus, strength, toughness, and temperature resistance. It's a very successful high-performance fiber in the Aramid family. You see how this fiber is produced. A similar method of a Nomex fiber manufacture, we manufacture the Kevlar also. So here you see this is synthesized by the condensation, which is the low temperature polycondensation, where a less temperature is used. The precursors or the raw materials used are the PPD, which is the paraphenylene diamine. You can see here two amine groups are there, but it is in the para position. It is the paraphenylene diamine and terephthalonyl chloride. You can see here COCl, COCl. It is an acid chloride. A diamine and a diacid, these both are reacted in a mixture of a solvent, which is the hexamethyl phosphoramide and N-methyl pyrrolidone. You can use the solvents in a mixture, and then you can produce the PPTA, which is the polyparaphenylene. Because of this para position, what happens? It leads to more intermolecular registration. That is why you get the good mechanical properties, and it becomes more crystallizable and has a high strength and modulus. Okay, so here, as I have already told you, this polycondensation reaction, unlike the normal polycondensation reaction which we carried out for the polyester, it is different because here we use a low temperature polycondensation, because it will lead to higher melt viscosity, which we are not interested with. That will not lead to the production of the fiber with a good strength. So we use a low temperature polycondensation to avoid the degradation and to minimize the side reactions. So what we do is we mix all the reactants and stir it, and so that what we do is we manufacture the Kevlar fiber, and then other processes like after treatments like grounding in the water, filtering it, and polymer whichever is obtained, that is washed, dried, so that you produce the polymer. Okay, some solid polymers pellets you produced, and here this fiber, unlike the Nomex fiber, this Kevlar fiber has an important feature that we are going to see now. So here there is a term called intrinsic viscosity. Hope you may be knowing what is an intrinsic viscosity. So for every fiber, this intrinsic viscosity will be there. Like for polyester also, some intrinsic viscosity is there. Then only it is recommended whether it can be used for the apparel application or it can be used for the technical fiber application. Or you see there is another term called the melt to flow index for the polypropylene, whether it can be used for the apparel or it can be used for the technical purpose. That is decided based on this viscosity. So the polymer of minimum intrinsic viscosity of say 4 deciliter per gram, it is preferred for the satisfactory fiber. So the viscosity should be minimum of 4 deciliter per gram measured in sulfuric acid. That we are going to see what is the importance of this viscosity in these fibers. So here you see this fiber, we are going to use the same technique like a wet spinning or a dry spinning, but some change is there in the manufacture. Some important changes we are going to make in this manufacture. If you see, this is the solid structure which you can see here, solid crystals, and these are the liquid crystals, and this is the complete liquid. Okay, so here you see this Kevlar, it exists in the form of a complete solid or in the form of a complete liquid, or it can be in the form of a liquid crystals. Okay, so here what is this liquid crystal that we need to understand? It is actually, it is not a solid phase or it is not a liquid phase, where solid phase has a certain shape and whereas a liquid doesn't have a certain shape. It will occupy the place where whichever container it is placed. Okay, so but whereas this liquid crystal, it is an intermediate between solid and the liquid. You know, solid will be a highly crystalline type of a structure, but whereas a liquid will be like an isotropic, where the properties, same properties in all the direction will be there. So but whereas a liquid crystal is something in between the solid and the liquid. Okay, if you just observe this in the microscopic level, it will be something like this. You can see here some rod shaped liquid crystal domains you can see in the spinning dough. So why we are producing this liquid crystal, that we are going to see now. This liquid crystal of the Kevlar, before that is, I am speaking about manufacturing of fiber. Okay, after you produce the Kevlar polymer, that polymer you need to spin into fibers. That polymer, after, how will you convert it to fiber? You will just dissolve it in a solvent, correct? You will dissolve it in a solvent, any kind of a solvent you will take and dissolve it in some particular concentration of the polymer you will take and use some temperature, and you will dissolve it so that you will produce a dope, which is the spinning solution. So here this PPTA or the Kevlar, it forms the liquid crystal only at a particular concentration, temperature and solvent and the molecular weight. Only at the certain conditions this is produced. Okay, if you observe, you can see here this graph which is shown here. In the x-axis you see the concentration and y-axis you see the viscosity. Okay, so you see here at a particular, if you go on increasing the concentration of the PPTA and sulfuric acid solution, because here in the sulfuric acid only we dissolve it. Okay, so here if you go on increasing the concentration, at the low concentration it increases, the viscosity increases, and at a particular concentration the viscosity is very high. Okay, and then what happened, it then start reducing, you can see here. Okay, and around again at 20, after reaching after it drops to 20%, then again it increases. Okay, so here this liquid crystalline nature, why we are interested in this liquid crystalline nature? Because liquid crystalline nature, it has to it has to achieve this polymer dissolution, the particular spinning dope, where the 100% liquid crystalline state is achieved. That actually leads to the molecular orientation in the spin line. Okay, and that happens only when the viscosity is at this particular concentration. You can see here around 20% concentration, the particular viscosity, whatever it is achieved, that concentration only this liquid crystalline nature is observed. That is what is shown in this graph. You can see here the uniformly it is the nematic crystals which is shown here, it is oriented. So because of this, what will happen, it produces the fiber with a good molecular orientation, and that happens only at a particular viscosity. Okay, so for this reason we dissolve this. Normally we take around 20% polymer and dissolve it in the 100% sulfuric acid, so that we get the liquid crystalline state. At this state only the maximum anisotropy occurs, spans different properties at different directions, so that you get the fiber with the good mechanical properties, the higher strength, the higher modulus. These things could be achieved when you maintain this liquid crystalline nature, and that will happen only when you take the polymer concentration of a particular concentration and particular temperature, and you will get the liquid crystalline state. Okay, so that is what is shown here, where as the concentration increases, there is an increase in the viscosity until some critical concentration is reached, after which the viscosity drops. So this critical concentration where this crystal formation, or you can say it is a nematic crystal, okay, which is the intermediate between the solid and the liquid. So that formation, wherever it occurs, that is the important thing which we need to notice here. So the critical polymer concentration needed for this crystal formation, it is dependent upon the molecular weight of the polymer and the temperature of the solution. So these things, if we maintain, what will happen? We can make a polymer dope that is suitable for spinning, so that from that spinning you will get the fiber with the good mechanical properties. Okay, so that is possible. That is the reason why we have been discussing in the past 3 slides the importance of the liquid crystals. Okay, so this is also a part of wet spinning, but slight difference in the manufacture, where the spinning dope, the solution, it is a liquid crystal spinning dope. Okay, because of producing this only, we get a higher molecular, higher orientation we get. So if you see here, whatever concentration we got the liquid crystal polymer dope we prepared, we do the wet spinning. You know very well how the wet spinning is done. I need not explain you further. So when you do the wet spinning, what you do, you will just take the solvent and then just extrude it in the air. You will maintain some small air gap here, and then here, once the fiber just get extruded into the atmosphere, and there it is pulled, and then it will get wound. It will just get wound, and then it will actually pass through the quenching chamber, where there will be a water bath, which is a non-solvent, to remove the solvents and the other organic salts are there that will get removed in the water bath. So that what will happen, the two-way mass transfer is observed, so that whatever liquid crystal is formed, that will get pulled and then it will get oriented. Okay, so here you see the crystals, every small molecular crystals you can observe here. These crystals, when it exits from the spinneret, it will get deoriented and then reoriented, so that finally when the fiber, before getting finally wound, that will get proper orientation. Okay, so that is the reason why we produce these liquid crystals. Okay, so that what will happen, some alignment take place. If you observe here it is not aligned, but whereas after it exits and if it is pulled, all the liquid crystals get aligned, so that leads to the uh, higher strength. Okay, so this is about the manufacturing of Kevlar fiber. This is very important, which you need to know how this Kevlar fiber is manufactured. So coming down to properties, Kevlar, it is a strong fiber, very strong fiber. It is strongest textile fiber available today, and it has a high tenacity, 22 to 26 grams per denier, and breaking elongation of 2.5 to 4%. And it is a dense fiber with a density of around, say, 1.44 to 1.47 grams per cc. And this fiber also, you see, there are more carboxyl and amino groups are there. So this also has a same amount of moisture regain like a Kevlar fiber. And you see, this fiber also has a high aromaticity, so this fiber is also difficult to ignite. And this fiber has a higher melting point and higher glass transition temperature, so around 370 degrees the glass transition temperature. So these fibers do not burn, but it will carbonize at a higher temperature of around, say, 425 degrees centigrade. But yes, it is a inherently flame retardant fiber. And what about the chemical properties? Chemical properties, it is unaffected by most acids under normal condition. It has a good resistance to alkalis and solvent, but not resistant to bleaches. Bleaching agents can affect the Kevlar fibers, and it has an excellent resistance to mildew and aging. But there is some problem associated with this Kevlar fiber. If you just expose the Kevlar fiber to sunlight for a long time, it will lead to photo degradation. Okay, so these fibers have this problem. Okay, that UV resistance of the Kevlar fibers are actually poor when you compare with the other fibers. So that has to be taken care of by you have to add some UV protection agents during the manufacture. And what are the applications? There are applications is decided by the end use what you need. There are many end uses are there. Wherever you require the high strength and modulus and flame resistance, there these fibers find use. Okay, for example, in the tire manufacture, there are in the tire manufacture, tires, when it is just rolling over the road, lot of friction is created, so temperature is created in the tire. So for making the tire cords, these Kevlar fibers are used for race tires, like a radial type of a tire. In tires, there are different types, like a radial tire or a cross ply tire. This is one of the radial tires. These tire cords, Kevlar fibers can be used. Conveyor belts can be used, one of the important application. And high power transmission belts can be used as a reinforcing component, because this fiber have a high strength. So this can be used as a reinforcing components. And the composites, yes, in composites it has a great application where as a reinforcing components, this Kevlar fibers can be used. Aircraft parts, the aircraft, these parts can be manufactured by Kevlar fibers. And other high performance products, especially like a reinforcing fiber or yarn, ropes, and cables, and you see bulletproof vest, ballistics, this can be used, and friction products like that. Plenty of applications are there, where only I have discussed a very few because of our time constraint and our syllabus point of view. But there are plenty of applications are there for the Kevlar fibers. Wherever you require a high strength and high modulus with the flame resistance, there this Kevlar fiber finds its application. Okay, so that's all about the Aramid fibers. Here we are in this high performance fiber lectures, we will be discussing, as I've already told you, the three fibers. One is the Aramid, carbon, and glass. We are just seeing the overview. We are not going in detail about each and every fiber manufactured. We are just observing the overview. So for all these fibers, you should know how this fiber is manufactured, what is the polymerization method, and what are its physical properties, chemical properties, and application. The overview you need to understand. So that's all about the Aramid fibers. If you have any doubt, you can ask. Otherwise, we can stop here for today.